Welcome friends. In the previous lecture we have explored the idea of deducing the transfer functions for single input single output system as well as multi input multi output system. Going further, we will explore today the situation when we have a very complicated system with several subsystems connected together in an integrate way, and we want to find out the exact transfer relationship between the input and output in the S domain. So to simplify such a situation, we have several approaches, and two commonly used methods are: number one, the block diagram reduction technique, and number two, the signal flow graph and Mason's gain formula. So we will learn both these techniques one by one and eventually judge which technique will be preferred in our case. So let us start with the conception of block diagram reduction technique. So block diagram reduction technique is quite straightforward, and you can see that there are several basic ideas and basic techniques which combine together to work out a big complex system, to settle it into or resolve it into a simpler form so that we can express the transfer function relationship between the input and output. So the bigger and complicated connection of the branches of a big system can be represented by equivalent simplified connections. So we take the situation where we have the original diagram and an equivalent simplified diagram. So we'll compare the situations in both the columns. So suppose we have the original diagram as a signal x1 entering a summing point where x2 is entering with negative signal. This is plus, so the combined signal should be x1 minus x2, and again the next node we have two signals entering, that is the x4 and x3. x3 is entering with negative sign and x4 is entering with positive sign. So eventually we are having x1. So here also we have positive sign for x1 minus x2 minus x3 plus x4. So an equivalent diagram for this can be like this. We have the signal x1 which is having a positive sign, then because x2 and x3 both are having negative sign, we combine together, make it x2 plus x3, and this together forms x1 minus x2 plus x3, sorry, minus x3, then that is added to x4, so it forms x1 minus x2 minus x3 plus x4. So both the diagrams are equivalent. So next diagram is, suppose we have G1, and the signal X is entering G1, and after G1 the signal formed is G1X. So this is summed with another signal which is passed through G2, but the input is same as X. So these together are added at the summing block and we get G1X plus G2X. So the equivalent should be, we have G1 plus G2. So the signal X is entering the block with G1 G2 and the result is definitely G1X plus G2X. So we try the other blocks. So the next situation should be X1 is entering. So I have the signal X entering the block G1. So the output is definitely G1X, and this is again entering the block G2, block G2. So this is definitely G2, G1X, and when this is made equivalent to G2, G1, so we can see that if X is entering, so output should be G2, G1X. Next example is the block G is having an input X1 and this is entering a summing block. So I have a plus sign over here, but it is definitely this GX1, and here we have minus sign and X2. So here the output is GX1 minus X2, and we have the equivalent as X1 plus minus sign 1 by G. This is X2 then G, and then we have X1 G minus X2. So this is the G. So when G is entering, we should have this signal as G X1 minus X2, because this G, this 1 by G X2 is nullified by this G, so X2 will not have any coefficient other than 1. So this is Gx1 minus X2. So both the diagrams are equivalent. So next example, the case is, suppose I have X1 x1 entering a block and x2 entering the same summing point but with a different sign. So we have x1 minus x2, and this is entering the block G. So we have G multiplied by x1 minus x2. So this is equivalent to the situation where I have x1. So I am shifting the point x2 over here like this. So this is opposite to the situation where I have shifted the point x2 before the block. So here I am shifting it after the block. So when I am shifting the block, this is shifting before the block, shifting what? Input. This is shifting input after the block. So after block G, if you shift the input, so this summing point will have only one input, that is x1, then G, then we have another summing point here. This should be plus, and because here x2 is forwarded, so the effect of x2 will be lost because of the gain G is not multiplied, so we have to send x2 with the gain G multiplied. So here I am multiplying the gain G with x2, because of the negative sign we have to give here negative sign. So output should be the same. So output should be gx1 minus x2. Now is the case that you are shifting the takeoff point from front of the block to back of the block. So I am shifting the takeoff point. G is there, X is there. So here definitely you have Gx, and the takeoff point I am getting Gx. So I want to shift the takeoff point from here to here. So what will be the effect? So because I am shifting the takeoff point, so the information of G will not be incorporated, so I have to incorporate the information of G separately. So here I have X, here I have Gx, but this takeoff point is going here, so the information of G will be lost, so I have to give a block of G, then I can take Gx. So this is how the takeoff point is modified. Similarly, if I am taking the takeoff point from behind G to the front of G, so here X, I have a takeoff point which is giving X. So after this it is Gx. So if I am shifting the takeoff point from behind G to the front of G, so I have to divide by G so that the effect of G should be removed. So I write it 1 by G, then it becomes X. So another two concepts we will explore. These two concepts are, first is you have the positive feedback closed loop path. So we have already studied this concept, although I am revising here. So if this is the summing point, this is entering as plus, this is also entering as plus, so this is equivalent to G divided by 1 minus GH. So if you can revise the previous video lecture, you will see that we have already worked out this concept. Similarly, there is summing point where x is entering and x1, x2 and feedback signal is negating at compared at the input. So here this is equivalent to g divided by 1 plus gh for negative feedback system. This is the situation, this is x1 and this is x2. So with the knowledge of these basic transformations and simplifications, let us try to reduce a big block into a simpler equivalent single block. So I am drawing a block which is relatively big in size. I have the R, the summing block, summing point, then G1, then G1, then I have another summing point where some signal is coming and compared over here. Then I have G2, then you have another summing point, some signal is coming and added over here. Then you have G3, this is G3, and here we have some takeoff point, some signal is going out, and then I have G4, and that is going to the output Y. So from Y I am getting a takeoff point with feedback filter H1, that is going to this point. So the takeoff point is above is having a filter H2, and that is going to be compared at this point. And another one is the takeoff point of Y, then that is going to filter H3, and that is compared at the input reference. So if this is the block diagram, let us see how we can simplify it. So to start with, the first step is to shift this point to this point. So because this is going ahead of this, so the information of G4 will be multiplied with H2. So to nullify it, we have to divide by G4. So let us do it in an innovative way. So this is our diagram, and we can remove certain points and make the things available for us. So this point will become this is H2, so this should be divided by G4, then this block is shifted here. So H2 by G4, this block is shifted, the takeoff point is moved, and once the takeoff point is moved, we can see that this portion can be simplified. How it can be simplified? We have the blocks over here, these blocks are actually together with the summing point. So from this summing point, we can find that this is a positive feedback system. So if this is a positive feedback system, then we can modify this portion. So I can say that we can modify this portion, and this portion will be modified, and removing this portion, and instead of this I am putting an equivalent block over here, which should be the single block of the positive feedback system, because the G3 and G4 will come together. G3 and G4 will come together, so G4 is the output block, so we will write like this, and the positive feedback path will have H1, so definitely we will have minus G4 G3 H1. So this we can combine together like this, and after this, the next we can combine these together. So if we combine this together, we can find another block, which is actually let me delete this block, and instead of this block we can write over here the block with G4 G4 G3 G2 divided by 1 minus G4 G3 H1, and this is a complete block at this point of time. So you can say that this is the equivalent. So again, this complete thing is a negative feedback system. So therefore, we can find out an equivalent of this block. So we have to find out the equivalent of this block. So I'm removing this complete block, instead of this we can have, after simplification of the blocks, you can write, I will expect students to solve it out, and here to save some time I am solving it and writing the result directly. So we have G4 G3 G2 divided by 1 minus G4 G3 H1. This will be the equivalent of the block, this one. So sorry, I have made some mistakes in writing the values. It should have the equivalent of G4 G3 G2 divided by 1 minus G4 G3 H1 plus G3 G2 H2. this will be the complete block, and from here I can see that these two blocks can be combined together. So if we combine it together, so we can write it in the form of, because this is the output block and this is the input block, so G1 will come to the right of this, so we can write it like this. Let me remove the block. Then I can place G1 over here. This G1 I can place over here. So eventually this block is again a negative feedback block, which can be written equivalently to, so this is equivalent to the block. If you can take negative feedback system simplified by the formula G4 G3 G2 G1, so this should be divided by 1 minus G4 G3 H1 plus G3 G2 H2 plus G4 G3 G2 G1 G1 H3. So this is the equivalent block of the problem taken in the beginning. So this has input R and this has output Y. All these functions are in S domain. So we have dropped the S for simplicity, but this problem you should solve at your own and try to find out that the equivalent transfer function is same as what you have deduced. So similarly, another problem I suggest you as homework, and you can take it and solve it and send it to me to my email ID. Let us consider the problem. So I have the input R, which is entering a comparator, this, and some negative signal is coming from other side. Then you have the G1, then you have another comparator, and that is summing two signals, and the output is going to another comparator, that is comparing two signals. Then output is going to a block whose gain is G2, its output is going to another block whose gain is G3, its output is going to another block whose gain is G4, and then comes the output Y, and between G3 and G4 there is a takeoff point from where through filter H2 I am sending a signal to this point for comparison. So then the output can be taken through a block H1 by G2 to reach the summing point where it is summed up. Another component of output is taken through the filter H3, and which is compared with the main reference input. So try to solve this block and find out the equivalent transfer function and send it to my email ID. You already know it is control systems faq@gmail.com. So this much is for today, and in the next class we will see how to work with the single flow graph and Mason's gain formula. Thank you for your patient listening.